Hello children, today we are going to learn about resistivity of various materials and its temperature dependence. So, what is meant by resistivity? Resistivity is the opposition to flow of electric current. Opposition to flow of electric current. It varies from material to material. Varies from material to material. So, what are the factors that resistivity of a substance will depend upon? Temperature. Okay, depends upon temperature. So, how do we classify materials based on resistivity? So, we know that different materials ke different resistivity irko. How do we classify materials based on their resistivity? So, we know that solids are classified as conductors, insulators, and semiconductors. So basically, conductor na enna? The material which allows current to flow through them, which allows conduction of electric current, are called conductors. Example, another conductors ke metals. Okay, metals are good conductors. They have very low resistivity compared to other substances. Idoda resistivity range will be 10 power minus 8 ohm meter. You know that the resistivity SI unit is ohm meter from the previous class. If you have not gone through the previous class, please watch the class. So from 10 power minus 8 ohm meter to 10 power minus 6 ohm meter. So copper and aluminum have very low resistivity and they are used for making wires for transporting electric current. For over long distances, the loss will also be very less. Okay. Now coming to insulators. What are insulators? Insulators are materials which do not allow electric current to pass through them. The examples, glass, mica, bakelite, etc. So they have very high resistivity. Insulators, they do not allow electric current to flow through them. Appa enna ho? Their resistivity will be very high. They are used for blocking electric current, opposing electric current. Okay, resistivity will be very high. And the resistivity will be in the range of 10 power 18 ohm meter greater than metals. Okay, it's very, very high. Semiconductors, as the name says, semi, they conduct for some time, they do not conduct for some time, depending upon the temperature. Okay, so these are the resistivity of semiconductors will lie between conductors and insulators. Any examples for semiconductors that you know? Germanium, silicon. Okay, they are typical semiconductors. And to improve the conductivity, we add some type of impurities, which is called impurity, means adding some other substances to it. This process is called doping. You will be learning in detail about this while we are discussing chapter 14, which is specifically designed for semiconductors. Okay. So the resistivity of semiconductors will lie between the range of 10 power minus 6 ohm meter to 10 power 4 ohm meter. Okay. So electrical resistivity is the opposition to the flow of electric current, first point, and it will vary from material to another material. It will depend upon the temperature. So generally, based upon the conductivity, we are classifying substances into three categories: conductors, insulators, and semiconductors. Conductors allow electric current to flow through them. Example, metals. So the resistivity is very less, in the range of 10 power minus 8 ohm meter to 10 power minus 6 ohm meter. Example, we said copper and aluminium, right? And then the next comes insulators. The resistivity is very, very high. They do not allow electric current to flow through them, and the resistivity is of the order of 10 power plus 18 ohm meter. Semiconductors, the conductivity lies between conductors and insulators. The range of resistivity is 10 power minus 6 ohm meter to 10 power 4 ohm meter. Again, to improve the conductivity, when you increase the temperature, the conductivity of a semiconductor increases. Okay. So this is the typed version of what we discussed till now, the summary of what we discussed. So here as we discussed, we can see that resistivity decreases with increase in temperature in a semiconductor. Okay. Now we are going to see the dependence of temperature on resistivity. We know like we have classified substances as metals, alloys, semiconductors, insulators. So first we will be seeing the dependence of resistivity with regard to temperature for metals. Okay. You all know that in metals, under the influence of an electric field, electrons start drifting in the direction opposite to the direction of the electric field, right? So those who have not gone through those classes, please go through it so that this class will be easy for you. Okay. So now, when you increase the temperature, what will happen here? These electrons will occur more energy. If energy increase, they will start colliding more faster compared to the normal state. The vibration will also increase. Vibration of the metallic ions will increase. So the electrons will collide more frequently, and the relaxation time, that is tau, will decrease. Okay, I hope you remember this relaxation time. You know that resistivity is given by M by N E square tau, and resistivity is the inverse of conductivity. Okay. So now when tau decreases, what will happen to resistivity? It will increase because they are inversely proportional. The resistivity of the metal will increase and the conductivity will decrease with increase in temperature. Okay. So resistivity is proportional to 1 by tau. So when tau decreases, resistivity will increase. So for most of the metals, resistivity will increase linearly with the increase in temperature around and above the room temperature, then above the normal temperature. So the relation between resistivity at any temperature can be given by the relation rho is equal to, or you can take rho T is equal to rho naught into 1 plus alpha T minus T naught. So this T naught is the reference temperature and T is the temperature at which you are measuring the resistivity. Again, rho T will be the resistivity at the required temperature and rho naught is the temperature rho naught is the resistivity at the reference temperature. Rho naught is the resistivity at temperature T naught. Alpha is the coefficient of resistivity. Alpha is the coefficient of resistivity. Unit of alpha coefficient of resistivity will be per degree Celsius or per Kelvin. Okay, anything is fine. Now, what is this coefficient of resistivity? It is a parameter that tells us the increase in resistivity per increase in temperature. Increase in resistivity per increase in temperature. Okay, it is a factor that tells us the increase in resistivity per increase in temperature. And for most of the metals, this value alpha will be positive. Okay, now take this equation. You know that rho is equal to R L by A, right? So now if this is for a single conductor, right? So L and A will be same. So R rho T, sorry, this is wrong. You know that R is equal to rho L by A, correct? Okay, so substitute that here. You will get rho T L by A equal to rho naught L by A into 1 plus alpha T minus T naught. So this can be written as RT. This can be written as R naught. So RT is equal to R naught into 1 plus alpha T minus T naught. These two formulas are very important in solving numericals, be it for CBSE examination or JEE examinations. So you have to remember these two formulas. Okay. Now coming to the typed part. So with the increase in temperature, resistivity increases and the conductivity decreases. We saw how it is being done in this slide, right? What happens to the collision and how the resistivity increases when the temperature increases. The resistivity over a limited range of temperatures. This is a formula that we discussed earlier. So rho T is the resistivity at temperature T. Rho naught is the resistivity at temperature T naught, or you can take this as the reference temperature also. Alpha is the coefficient of resistivity. SI unit is per Kelvin or per degree Celsius. Okay. And for metals, this value of temperature coefficient of resistivity is positive and it is nothing. It tells us the increase in resistivity per degree rise in temperature. Okay. So, yeah. So now to find out, if you are given other data and asked to find out alpha, alpha can be calculated like this. Rho T minus rho naught divided by rho naught into T minus T naught. This is done by simplifying this equation. So this is a picture diagram showing you the variation of resistivity of metal with regard to temperature. If you can see here, this region is a nonlinear region, right? Yes. So this, what is the temperature here? It is 50 Kelvin. That means what is its like value in Celsius? It will be very less, right? You know the like conversion between, I hope you know the conversion between Kelvin and Celsius scale. So this in Celsius scale, if you see what will be this temperature, the temperature will be very low. So the resistivity of a pure metal increases when the like what is the temperature is low. Okay. And this is in Celsius, it should be below 0. Right. Okay. So this is for pure metal. This diagram is for pure metal. For temperature 50 Kelvin means when you subtract, you have to check the value of in Celsius scale. That is, it is below 0. So that what happens is the resistivity is non-linear and the variation is also high. Okay. Now coming to alloys, you all know what is an alloy, right? Alloy is a combination of substances together. Okay, alloys, how will be the resistivity of alloy? The resistivity of alloy will be very high. Okay, and they will have a very weak temperature dependence. Some substances will have, they will be almost independent of the temperature also. So now, if you can see here, you can see that nichrome exhibits a very weak dependence of resistivity with temperature. Similarly, manganese and constantine also. Okay. So they are used in wire-bound resistors. You know what is a resistor is. Okay. And this is the conversion from resistivity to resistance, which we discussed. Here there was one more quantity. RT is equal to R naught into 1 plus alpha T minus T naught we discussed there. Right. So when there is no reference temperature, then you can reduce this equation to this. Okay. So summarizing, alloys will have high resistivity. They are almost having a very weak dependence on the temperature. So they have they always have high resistance. Okay. So this is the temperature graph showing the variation of resistivity of nichrome with respect to temperature. Here also, sorry, nichrome, right? NaCHRON, nichrome. Okay. Now coming to semiconductors. For semiconductor, the resistivity will decrease with increase in temperature. As I told you, the conductivity will increase when you are when you are increasing the temperature, so that the resistivity will decrease. This is the formula that we saw on the first sheet. Rho is equal to m by ne square tau. Okay, that is resistivity is the inverse of conductivity. Okay, I hope this is understood. So now with this basics, we are going to solve two numericals, which is based on the formula that we discussed. A nichrome heating element connected to a 220 volt supply draws an initial current of 2.2 amps, which settles down after a few seconds to a steady value of 2 amps. Find the steady temperature of the heating element. Room temperature is 30 degrees Celsius and the average temperature coefficient of resistance, that is alpha, is 1.7 into 10 power minus 4 per degree Celsius. Please write the given data first. So given V is equal to 220 volts, right? V is 220 volts. Then you have current, initial current I1, I am taking it 2.2 amps. Then I2, the steady current is 2 amps, 2.0 amps. Alpha is 1.7 into 10 power minus 4 per degree Celsius. So now you have to find out R1 and R2 for I1 and I2. So resistance at room temperature 30 degrees Celsius. Okay, resistance at 30 degrees Celsius, R1 equal to V by I1. So that is 220 divided by 2.2. So you will get 100 ohm. And resistance at steady temperature. Okay, steady temperature, right? Settles down. Steady value is given here. that you can take it as R2, which is V by I2. So your value of I2 is 2, right? So 220 by 2, that is equal to 110 ohm. Now using the formula for alpha, write the formula for alpha first. Alpha is equal to R2 minus R1 divided by R1 into T2 minus T1. Okay. So if you have doubt regarding the formula, please go back and check. We have to calculate. What are we supposed to find out? You have to calculate the steady temperature. Okay. So that is steady temperature means you will be calculating T2. So that what you will do is you will bring this T2 minus T1 here and bring the alpha down. R2 minus R1, right? Divided by alpha into R1. Now substitute the values. Then you can substitute T1 and add. So that it will be. See, R2 is 110. R1 is 100 divided by alpha is 1.7 into 10 power minus 4 into R1 is 100. So you get a value of 10 divided by 1.7 into 10 power minus 4 into 100. So 1.7 into 100 is 170. 170 into 10 power minus 4. So when you are dividing this, bring this 10 power 4 to the numerator, minus 4 to the numerator, it becomes 10 power 5 by 170. So you will get it as 588.23. Okay. So you can round it off to 588 degrees Celsius. Okay. Now, this is T2 minus T1, right? So when you wanted T2, T2 will be 588 plus T1. What is your T1 value? Check the question. T1 value is 30 degree, right? So when you are adding, you have to add that 30 with this. So 588 plus 30. What will be your answer? 618 degrees Celsius. Okay. So here one rounding off we have done. So this is the temperatures of the steady value. Okay. I hope you have understood this question. You can practice a lot of questions in this method so that it is easy for you. Coming to the next question. The resistance of a tungsten filament at 150 degrees Celsius is 133 ohm. What will be its resistance at 500 degrees Celsius? Temperature coefficient of resistance is given. So now first write the data. Resistance at 150 will be equal to 133 ohms. Alpha value is 0.0045 per degree Celsius, right? We have to calculate the resistance at 500 degrees Celsius. So you know that RT is equal to R0 into 1 plus alpha T. So R150, if you calculate, what will be the case? R150 will be equal to R0 into 1 plus alpha into 150. So that will, you can write it as R0 into 1 plus alpha value is 0.0045 into 150. Take this equation as the first equation. Okay. And you can rewrite this. What is the value of R150? 133. So 133 is equal to R0 into 1 plus 0.0045 into 150. Take it as equation number 1. Coming to the second part, you have to write for R500 in the same manner. So R500 will be equal to R0 into 1 plus alpha into 500. That is R500 is equal to R0 into 1 plus 0.0045 into 500. Okay. So now this equation, you can take it as equation number 2. You do not know R500, so let it be as this. Now divide 2 divided by 1. So it will be R500 divided by R150. That is equal to R500 divided by 133 ohm, right? R150 equal to R0 into 1 plus 0.0045 into 500 divided by R0 into 1 plus 0.0045 into 150, right? Okay. So R0 and R0 will get cancelled. So this, when you multiply this, you will get a value of 2.25. So you will get it as 1 plus 2.25 divided by 1 plus 0.675. Now when you, this is R500 divided by 133. Right. So now this is 3.25 divided by 1.675. So now when you want to find out R500, right? R500 will be equal to 3.25 divided by 1.675 into 133. Okay. So when you substitute this and solve it, you will get an answer of 258 ohms. Okay. Please check your answer. Try to solve it. Go through this and try to solve it by yourself so that you are able to do it by yourself. I hope you have understood the concept of electrical resistivity and how it varies with regard to temperature. If you have any doubts, please raise to us in the comment section. We'll be happy to help you. Thank you.